Okay, so this problem is actually pretty similar to the previous problem. It just has a little bit more. So we're assuming that demand is linear today, and the homework problems will also assume it. So let's look at this. Let's say we have some sort of venue and they're charging $50 per ticket to some concert or to a series of concerts. And when they did this, they averaged an attendance of about 4,000 people. And then maybe the next year or like some other similar comparable statistical thing. So we're not comparing like Tuesdays and Saturdays, right? Some other time they increased the ticket prices to $52 and the attendance dropped. What price should they charge to maximize revenue? Okay, so again, we could kind of look at, okay, what was the revenue in this situation? $20,000. Nope. $200,000. 50 times 4,000. All right, what was the revenue over here? Oh, I have no idea. It was 3,800. Oh my word. $197,600. So increasing the ticket price made us less money. So the question is, all right, where's that sweet spot? Increasing by $2, that wasn't the call. But where's that sweet spot? What should we charge to maximize revenue? And so, again, this is kind of in isolation. If we have to charge like $49.32, we probably aren't actually going to do 32 cents. We'll maybe round it to $50 and then charge, have like a $50 online ticketing order convenience fee or whatever happens. It drives me crazy. So let's look at this. So just like before, right? The revenue, which is what we're trying to maximize, is still just, how many tickets times the price. So if we just let X be how many tickets we sell, and price be the price, is just the same before. The revenue is just how many things you're selling. What are you charging for each of them? Multiply them off. Multiply them together. The problem is, in the last example, we had a demand function. We plugged it in. We need our demand function. Okay, so that's how we're going to actually start this problem. We need to find the demand function. And the demand function is what relates how many people with the price. We got two little things right here that we're going to look at, right? $50 was 4,000 people. $52 is 3,800 people. So we're going to write these as ordered pairs. And again, it doesn't matter which one we solve for. It doesn't matter which one we call our X. You can choose whichever one as long as you're consistent. All right, so when price was $50, we had 4,000 people. When price was $52, we had 3,800 people. Again, this first one is our price. The second one is our X. If this makes you uncomfortable, because usually X is the first one, you can switch the order on both of these and have 4,000, 50. All right, doesn't matter though. Just do whatever you're comfortable with. So I want a line. I'm looking for a line that connects these 2 points. That'll be our demand function. So how do I get a line from 2 points? A couple different ways. We need the slope, and then we can use point slope form. All right. Or we could find a slope and then the y-intercept. Either way, we certainly need the slope if we're going to relate these things. All right, so we need the slope. Remember that slope is going to be y2 minus y1 over x2 minus x1. Or in this case, our y is our x and our x is our p. So it's going to be the second coordinate, the difference in the second coordinate minus the difference in the first coordinate. In this case is x's and p's. All right, Jason, this is probably a bad choice. All right, so the second coordinate is x's. We need to find the difference in the x's. First coordinate is p's. We need to find the difference in the p's. So the second x value minus the first x value, 3,800 minus 4,000. Divided by the difference in the x's, 52 minus 50. Simplify this out, you're going to get negative 200 over 2, or just negative 100. Slope is negative. Does that make sense? Slope being negative means that if I increase P, X is going to decrease. Well, that makes sense. If I increase the price, fewer people are going to buy a ticket. And it should decrease by 100 fewer people for every dollar that I increase. And that makes sense. If I increased it to $51, we'd have 3,900. Increased to 52, that's another 100, 3,800. Okay, so this slope makes sense. Now we'll use point slope form. Okay. And our point slope form, again, we can choose any point we want. I'm going to choose kind of the nice one that when we charged $50, we had 4,000. And it's like the y coordinate, and again, really kind of messed you guys up here. The y coordinate is x for us. So it'll be x minus the 4,000 is equal to the slope, which is negative 100, times the x coordinate, which is p, minus the p coordinate, 50. And we can simplify this out and get a demand function. So add 4,000 to both sides, you're going to get 4,000 minus 100p plus 5,000. Or you'll get x is equal to 4,000. Nope, that's not how numbers work. 4,000 plus 5,000 is 9,000 minus 100p. This is also a demand function. In the last example, in the last video, we had a demand function where we solved for p. Here, this is a demand function that solved for x. Both are okay. Both forms are fine, right? It just affects what we're replacing. We solve for x, so our revenue is x times p. We'll replace the x part with this. So let's kind of summarize that on the next page. Right, our revenue, which we're trying to maximize, not minimize, Jason, is x times p. And we also know, right, oops, that x was equal to 9,000 minus 100p. Or again, every time we increase the price by $1, 100 fewer people are going to show up. What we're going to do is we're going to substitute, right? X is equal to that. So our revenue function is x, which is 9,000. All right, hold on, small thing here. 9,000 minus 100p times our price. And actually, this is not anymore a function of x, right? This is now a function of p. So we'll simplify this a little bit out. We'll take the derivative. We'll find the maximum. We'll get 9,000 p minus 100p squared. Take the derivative. Set it equal to 0. And we're going to get an answer. All right, so add 200p to both sides. We'll get that 200p is equal to 9,000. Divide both sides by 200, and you're going to get 45, I believe. So increasing the price was the wrong call. All right, here, the price is 45. It's saying what price should they charge per ticket to maximize revenue? So the price they should charge is $45. All right. And we're going to get, assuming we have the capacity to host this many people, we're going to have $45. So a decrease of $5 going to increase attendance by 500. We'll have 4,500 people paying $45. Kind of look at this. $45 and 4,500 people. That's 202.5 thousand. That's an extra 2.5 thousand if we lower the cost of a ticket. Extra 2.5 grand we're going to be making. All right. Good luck.